Hi, good morning. Today we're going to start the first chapter in the first section. We're actually going to do some math today. Well, because math is a language, we have to know the syntax, the words. For example, this chapter 1 deals with graphs, functions, and applications. Which words in that title do you understand? Do you know what they mean? Okay, let's go with that. Define graphs, or define a graph. What is a graph? No, doesn't have to be a grid. That's just one type of graph. I mean, you're not wrong, but you're not right because it's not a definition of graph. What is a graph? That's the data set. See, all these words. A graph is a pictorial representation of a function or equation. Function or equation. A graph is a picture. That's what pictorial means. It's a picture. It represents the outputs. What are the inputs and outputs of an equation, of a function? We discussed equation last time. What's an equation? What makes it an equation? There's an equal sign, right? So if you see something that has numbers and letters or words even, and it has an equal sign, that's an equation. That means there is a solution. If you have an equal sign, there is a solution. We're going to describe functions in a little bit. So equation versus expression. As we said, an equation has an equal sign. An expression does not have an equal sign. Equations, you're asked to solve the equation. And expressions, what are you asked to do? Simplify. So what does that mean? When I ask you to solve, what does that mean? Find the value of the variable, yeah. Find the value or the values of the variable. When you're asked to simplify, what are you asked to do? 3 letters. C L. That? Well, yes. It is in essence you're compressing it. You're asked to combine like terms. You're compressing, yes. You're making a large equation into a small equation by combining like terms. So in an equation, you're not done until the variable equals a number or a series of numbers. Yes, to have it, you have a series of terms. Okay, and I use the word terms twice. What does term mean? No, that's a variable. A term. Good try though. But see, what I'm getting at is this: is in these statements, in these sentences, we're using words that we understand, we know what they mean, but we don't know what they mean. We don't know the definitions. In mathematics, you need to know that. You have to associate the command, the word that's in there, with either an equation, a formula, or a procedure. So we have to know the definitions. That's what I'm trying to stress today. As we go through, you're going to have words associated with a formula, an equation, a procedure, but it's going to tell us what to do. A term is anything separated by a plus, minus, or equal. They can be numbers, letters, or both. Ooh, that's a question. There's multiplication and division combined. Remember, multiplication is a series of additions. So if I say 5 times 3, I have 3 plus 3 plus 3 plus 3. So I have 5 separate 3s. But when I multiply them, they're not really separate. One is combined with the other. So that's why a term is only separated by plus or minus. Remember, we're going down to the smallest levels of equations possible. For example, if I gave you that equation, how many terms do I have? Yeah, here's one term, 2 terms, 3 terms. And remember, now we know what it means when it says combine like terms. You look at how can we combine any numbers? We can't really combine when we multiply because it changes. When we multiply or divide, we change the shape of the term itself. For example, if I had x times x, what does that equal? X squared. It's no longer the same as my entry points. But if I had x plus x, what does that equal? 2x. My x's are still the same. This is like apple times apple equals a super apple, or apple plus apple is 2 apples. So it changes the function of it changes the shape of the term. Let's look at what a function means. A function is merely another way of writing an equation. A different way of expressing an equation. Bless you. With one main difference. The value of the variable is included in the function. It's a different way of expressing an equation. The only difference is that the value of the variable is already expressed in the function. A function looks like this. Here's an example of one. Remember I said It's the same as an equation. An equation would be written like this. How do we know that's a function? Because it has the name of the function, the value of the variable in the equation part, and you have the equation. It makes it much easier to write. Let me show you. Here, we got this. Image sorting. Here are examples. So if given y equals 3x plus 2, what is y if x equals 2? So what would you do there? Yeah, I would take, since anywhere I see an x, it equals a 2. So inside this equation, anywhere I see an x, I put a 2 in its place. Three times 2 is 6. 6 plus 2 is 8. So there's the answer. The problem is all this stuff writing up here. This is an example of an equation. The way you do it for a function is this way. You know it's an equation. There's an equal sign. So you know you're supposed to solve it. We know what the variable is. It's going to be equal to 2. So anywhere we see a variable in the equation, we put what in its place? You put a 2 in its place. Okay, that's not the only thing it's good for. What if I asked you for that? What would you do? Yeah, anywhere, because the function name is f. So anywhere you see the letter f as a function name, it equals to this equation. And in place of x, I put a -3. So I have 3 times x plus 2. So it's 3 times -3 plus 2. Positive times negative is a negative. 3 times 3, 9. There are two different signs, so what's the rule here? Take the sign of the larger number, which is 9. It's negative, so the answer is negative. 9 minus 2 is 7. So that's how functions work. It makes it much easier. And we can put a whole bunch of equations out there. I can ask you for all of these now. I don't have to write the equation over and over. I put x equals this. I just put this there and I'm done. So it's So a much easier way of writing it. So basically what it says that since the equation, it's the same thing as this. So the answer is the same in both of them. Whatever you're solving for is the same as both. Any questions so far? So now let's look at graphs. How did you first learn to graph things? In which grade? Earlier. First or second, right? That's exactly what it is. The first graph you ever did was a number line. If you think of the whole evolution of it, you first learn to do what? You first learn numbers, learn how to count. When you count, what do you start with? Yeah. So this goes all the way to positive infinity. So from 1 to infinity, we call those natural numbers. Or actually, instead of natural, you can call them counting numbers. And then you learned the number 0. The numbers 0 to infinity are called whole numbers. And that's pretty easy to remember because the 0 looks like a whole. It starts with a whole number and it goes on to infinity. And then we're taught negative numbers. Everything from negative infinity to positive infinity, just those numbers, no decimals or anything, we call those integers. Integers are just the numbers, -5, -1, +10. Nothing in between them. What do we call the numbers in between two numbers? They're called decimals. In mathematics, we call them rational numbers. And yes, those are the decimals. So now the rational numbers are everything from negative infinity to positive infinity and in between. Here's a statement. Every number is a rational number. That's a true statement. Every number is a rational number. Notice what it says is every number is a fraction. That's what it tells us. Because rational numbers, decimals are fractions. True? Of course you say true, but I just told you it's true. So every number is a rational number. Every number is a fraction. For example, the number 4. Is that a fraction? How? 4 over 1. Since it is a fraction, it's also a decimal. 4.0. So every number can be written in either one of these three forms. Why do we have to know that? Well, because when we start dealing with multiplication, division of fractions and decimals, we have to know how they relate to each other. That's all that next class is. We'll go over the rules of multiplying, adding, subtracting, multiplying, dividing fractions. So I know you guys love fractions. And I'm gonna show you a shortcut in this class. Is whenever you have equations with fractions, get rid of the fractions first. If you get rid of the fractions first, it's an easy cake. Yes. Nope. Nope. Again, if you had, let's say, 2/3 or 0.666666666, which one's more accurate? This one's not accurate because I only stopped here. How many more sixes are there? Infinite. There are infinite number of sixes. But here, this is already included in it. So this tells me exactly all the sixes in there. So that's why leave them as fractions a lot of times. Don't put them in decimals. Which is why calculators won't help you much. Because I want the answers in fractions, not decimals. All right. So we had natural numbers. Then we expanded with 0, we got whole numbers. Then negative numbers, we have integers. Then we had rational numbers, which is everything in between. Those are those are in a set, what we call real numbers. Real numbers, actually, I should show you all the symbols I use for those. Because real numbers is represented by that symbol. Kind of looks like the realtor symbol. For people who sell houses, the realtor. The real numbers are everything from negative infinity to positive infinity. Decimals, fractions, integers, whole numbers, everything. But they're real numbers. What's the opposite of real numbers? Imaginary numbers. Remember, if it's not real, it's imaginary. Imaginary numbers have that letter after them. And we're going to have a whole section just devoted to imaginary numbers. What's the definition of imaginary numbers? Literally, in every math book you'll see, the definition of imaginary numbers is not a real number. Can you graph imaginary numbers? Nope. It's, in other words, if imaginary number is like up here, you can't. It's not on the paper. It's in the third, fourth, fifth dimension plane. Can we combine the two? Can? What do we get? Well, that's still imaginary. Well, not always, but we'll get to it. But yeah, if imaginary, it's going to be imaginary. But the imaginary, the I can disappear. We can combine both of those. A real number plus an imaginary number equals what we call a complex number. Complex numbers look like this. You can't really combine them, but you can put them together. The whole thing, the whole reason we have imaginary numbers is because in engineering, in science, we can get some equations where inside certain equations, you get negative numbers where they can't be negative numbers. And if that happens, we can't say the whole thing is impossible because it works, like space travel. Traveling through space or the speed of light, all this stuff is possible, but we can't really explain it. So that's why we invented the concept of imaginary number. So that's the number line in a nutshell. So back to our little simple number line we learned in elementary school. If I said, tell me where 3 is, what would you do? Find 3, put a dot there. There's your first graph. How about if I said, show me where -2 is? You go here, the -2. But what's really happening? I know we'll look for these numbers down here, but what's really happening? The number 3 represents what? Well, no, number 3 represents a distance. You always start at 0. Because 0 is neither positive or negative, so you start at 0. If I say go to 3, what are you going to do? 1, 2, 3. I go to the right because the right is positive, the left is negative. So at -2, I got start at 0. It's negative, says I go to the left, 2 spaces. And then you learned subtraction. How would you do it? Remember, back then you learned reading left to right. So you go to 5, start at 0. 1, 2, 3, 4, 5. So we go 1, 2, 3, 4, 5. We put it out there. This one says go which direction? 6 spaces. So from here, I go left. 1, 2, 3, 4, 5, 6. So there you have it. So you learn how to add first, then we learn how to subtract. So that got pretty boring after a while. Because that really meant nothing. Then we learned algebra back then. How do we use number line to solve for x? Yeah, that's a big step, but you're right. We would subtract. We would start off at 5 and then subtract 3. But how do you tell this to kids? Yeah, so start at 3. How far do I have to go to get to 5? 1, 2. So that's what x has to equal. Because I'm adding them, going to the right both times. So that's again pretty boring. And if you think about it, Think of how humans traveled at the beginning. Walking, riding horses, riding bicycles, riding cars, riding wagons, boats. Everything's horizontal. And then we started flying submarines. So we started going up and down as well, which is why we need to discuss another axis. So there's your horizontal axis. That's your number line. If you go up, is it positive or negative? It's positive because you're increasing. If you go down, they're negative. This is what we're used to seeing. What is this thing called? Don't say graph. The plane is one of those things. Or he says an XY plane. I'll give you hints. We'll do. Oh, there's E already. Sorry, no. Yeah, no. I'll give you a hint. The first one is after somebody's name. Cartesian coordinate system. You would never heard. Did you ever hear the phrase "I think, therefore I am"?
No.
Rene Descartes is a French mathematician, philosopher, scientist who came up with that. He said, "I think, therefore I am." Cogito ergo sum. He came up with this grid system. You'll never guess how. With the help of a fever and a spider. He was sick one day, lying in bed, and he noticed one spider on the ceiling. And he said, I can tell you exactly where that is. By counting from one place, I can count how many beams over and how far down. So he said, he started thinking, I can now coordinate wherever I am on a grid. So he tells somebody, where's the spider? The spider is 5 over and 8 down. This is what we do here. That's why I call it the Cartesian coordinate system. Or the grid, or the graph, yeah, whatever you want to. But yeah, we don't have to call it Cartesian coordinate system. We'll just call it the graph. But that's where it came from, which is pretty cool. He was sick one day and just got bored. Remember, that's boring back then because they didn't have TV, they didn't have cell phones. So he had to do something else with his life. We have 4 of these things. They're called quadrants. Called a quadrant because there's 4 of them. How would you number them? Starting from here or here? What would you call this one? Very good. But why would you do it counterclockwise? Yeah. We call this counterclockwise. They had clocks, but they didn't have watches or anything. So they really discussed that. They used what to keep time a lot of times out there? Sundials. Where does the sun rise? East. The east is over here. And it sets in and there's the north, and there's the south. So the sun starts in the east, goes to the west, and then the moon follows suit. So there you have it. That's the reason it went counterclockwise to us. If we were to invent it today, we would have started here and gone this way. So now let's talk about what is a point? What's a point? What's the name for a point? A dot? I mean, what I asked you, okay, put a dot where this is, or put what's this point? What's the other name for it? Coordinate, very good. You know why they call it a coordinate? Co means with. What do we call the horizontal axis? What do we call it today? The x-axis. What do you call the vertical axis? They didn't call that back in the old days. That was called the abscissa. And this was called the ordinate. So together, they form a coordinate. This number went with this one. It was a coordinate. It's also a location. So any dot we put on there, so if I gave you this dot here, what's that location? So it's, how do I write 2, 1? Right. What do we call that? And it's not any of these words, no cheating. Very good. It's called an ordered pair. I had students in the past that would spell it this way. They must have been culinary students. They really thought that's what it's about. Because they said it's ordered pair because it was, I ordered a pair. No, it's a pair of points. And then what's this location? Can't get this one wrong. So an ordered pair is in the form of an XY coordinate pair. It's done the same way we did it on the number line when we were kids. It's done exactly the same way. What's this point in the middle called? This is called the origin. What's its location? It's 0, 0. Very good. So if I give you the number, the coordinate 2, 1, you start at 0, 0. So the first number is the x number. So I go 2 over and up 1. And that's, again, it all starts the same way we did it as kids. So tell me what quadrant these numbers are in. If I gave you what quadrant? I can put a 3 in there. It's the okay. You guys ready for this one? It's none. Because where is 2, 0? Right here. This is called an interquartile point. Because it's between two quartiles or two quadrants. So if it's on the x or the y axis, it's not on in any quadrant. So when you look at these numbers here, what went through your head when you tell me what quadrant it's in? First one tells me I go which direction? Left and up. Left up is second quadrant. Left down, third quadrant. So again, that's the same way we do this thing. Who do you think uses this kind of information? Yeah, besides my professors. Yeah. Carpenters, yeah. But who use it for their lives? Military, submarines. Think about it. I mean, if you're in a submarine, you have a fixed point. You're the submarine, that is you. Yeah, exactly. Well, then that's you. You go in two parts. But yeah, it's you could relate yourself specifically, go forward, up and down. And airplanes, same thing. Relative to where they are, they say, do I go up or down, left or right? What was I going to do next? I want to do that. I want to do that. Determining whether an ordered pair is a solution to an equation. What does that mean? Now that we have an x and y axis, our equations have to have an x and y variable. This represents the x-axis, this represents the y-axis. So is that that pair, ordered pair, a solution to this equation? How'd you do that? Did you plug it in already? So you guessed. Yes, you did. Now, yeah, try not to guess. We'll see this. So what does this number represent? Yes, yeah. So it's in place of x, I put a -4. And in place of y, I put 12. Now, if both sides are equal to each other, then that's a solution. If both sides do not equal each other, that's not a solution. It's either one or the other. So positive times negative is a negative. 3 times 4 is 12. Negative and positive. 12 is bigger, so the answer is negative. 12 minus 2. So it's not a solution. As I said earlier, last week, before you turn in any work or any test or anything, you should know yourself whether it's right or wrong by doing the work, by checking your answers. Is 517 a solution? You worked it out. But yeah, a lot of students fear it's a 50-50 shot. So I could hurry up and finish this class. Just guess. Yes, it is a solution. So I've replaced the X with 5. Remember, this is an X and that's the Y. And work it out. 3 times 5 is 15 plus 2. So that is a solution, right? Good morning, sir. Traffic.
No, could you check if I'm actually in this class? I'm actually confused.
Well, yeah, we'll do after class.
So I have this class 2 times.
In the same semester?
Yeah.
Well, yeah, I'll try to check after class. Okay, what if I gave you this equation? Is 0, 0 a solution to that equation? That didn't sound too confident. It was more like a question. No. Yes. Anything times 0 is what? It would just, there'd be nothing. There's nothing there. It's gone. How are you? Well, how did y'all solve this? Those of you who solved it. What did you do? Just plug it in there? That is one way. Let's see how that works. So we put, here's my X and here's my Y. We have no Y's, so that's okay. So just plug in anywhere we see an X, put a 0. Anywhere we see an X, put a 0. 4 times 0, 0. Negative 2 times 0, 0. So we have 3 plus 4 on that side. 2 times 0 is 0, so we just have 1. So does 7 equal 1? So 0, 0 is not a solution. Yes, but I don't suggest using that method. Let's use another method here. I'll put the same equation down. So now, whenever you have equations, before you do anything, Always simplify both sides first. Because we see this is a huge bunch of strung out stuff in here. Can we combine them? Yeah, so we have 4x minus 2x, so 4 minus 2 is what? So it's 2x. 3 plus 4, positive 7, equals 2x plus 1. We have x's on both sides. So we have to move, we can only solve it when x is on one side. Because remember, it's an equation. We have to have x equals some number. So we have to have x on one side. How do we move the x? Minus 2x. 2x minus 2x is 0. 2x minus 2x is 0. It's a lot faster that way. So your steps are really this. Combine like terms. That's the first thing we did. Then we have to isolate the variable. What does that mean? Isolate the variable. Get it by itself. And since we have x's on both sides, if x is on both sides, move the smaller one to the larger. Always. Why? I know most of y'all remember in high school, they said, always move the x's to the left-hand side. I'll show you why that's bad. Well, because if you move the x, sometimes you have a negative number in front of the x. And we want to keep away from the negatives. If you do this, move the smaller to the larger, we're always going to have a positive answer. A positive x. And we'll do some examples on these as we go along. Well, we'll do it now. Here's an example. We have so far only 2 steps in our process. What's the first step? On each side, can we combine anything else? No, so that's done. So step 2, move the smaller, since we have x's on both sides, move the smaller x to the larger. Which one do we move? -4, because -4 is smaller than +2. How do we move -4? We add 4 x to both sides. So -4x plus 4x cancels out. 2 plus 4 is 6. X minus 5. Do we have all the x's on one side? Yeah, so step 3 is move all non-x's to the other side. So which one do we move? When I say move all non-x's to the other side, I'm saying on this side, since all the x's are here, if it doesn't have an x, it goes to the other side. So we have to add 5. Since it's a -5, we have to add 5 to both sides. Those cancel. 3 plus 5 is 8, equals 6x. This is going to feel odd to you for some time because you're always used to moving x to the left-hand side. And that's where most errors occur. Because if I move the 2 to the other side, we'll do that in a second. I'll show you what we're going to do. But you don't always have to move to the left-hand side. You move it wherever it's easiest for you. Now what do? Multiply or divide by the coefficient of x. Because remember, we're trying to get the x by itself. So we have to get rid of the 6. How do you get rid of the 6? Divide. Because how is 6 connected to x? It's multiplied. What's opposite of multiplied? So we divide both sides by 6. And then simplify your answer. Can anything simplify here? What do they have in common? A 2. So 2 goes into 8 how many times? 2 goes into 6 how many times? So there's your answer. And now if you want to, you can flip it so it's x on the left-hand side if you want to. But it really doesn't matter which side the answer x is on.
Is it always going to be a fraction?
No.
No.
So what if normally what I do is, what if I put -9 here? If I put -9 here and we add 9, we get 12. So 12 divided by 6 would be 2. So no, it is basically the answer is what the answer is. Yes. Which one? Oh, if it was x over 6? Yes, if it was x divided by 6 on this side, we have to multiply by 6 both sides. Okay, here's a rule. What kind of fraction is this? This is called an improper fraction. Why is it improper? Because you have a larger number on top of a smaller number. Fractions, by definition, not by definition, are supposed to be between 0 and 1. For example, 3 over 4. That's a standard, a regular fraction. That's a proper fraction. But 4 over 3 is bigger than 1. So whenever you have an improper fraction, what do? Convert to mixed number. How many times does 3 go into 4? Once. With how many left over? Over the denominator is 3. There you have it. So 3 goes into 4 one time with 1 left over. And since 3 is the denominator, it has to stay there. So this is what your answer would look like. Much. I'm going off track here. But yeah, I want to spend a day and do nothing but fractions with y'all. Because that's where the biggest problems are going to happen. So let's go back. Let's get back on track. So we're looking at graphs. If I had this graph, and I had a dot here, and I asked you to draw a line through that, how many lines can you draw through it? Infinite number. Because you can draw that line. You could draw that line. You could draw that line. And so on and so forth. You keep on going forever. There's an infinite number of lines that can go through any one dot. So to draw a line, we need how many dots? We just had one. Yes. So to draw a line, we need at least 2 dots. Points. This would be mathematical here. We need to have 2 points to draw a line. And for the first part of this course, I'm going to use the same 2 dot points. So plot the point 1, 1 and 5, 4. Plot those 2 points. And we're going to be using these for the first part of this chapter. And we're lucky because we know both of those points in which quadrant? The first quadrant. So the first one is there. And then somebody asked yesterday, how do I know what the first point is? Because we have to name these points now because it helps us in the long run. How would you, where's the first point? Yeah. Why would you name it 1, 1? Yeah, pretty much when you're naming points, or you're putting dots from the origin, draw a vertical line, and as you go across the horizon, what's the first point you get to? 1, 1. So we're going to call that one point 1. And then we'll call the second one point 2. So point 1 has the coordinate 1, 1, and point 2 has the coordinate 5, 4. Now, can I draw a line through them? Only one line through them. We'll call that line 1. We have ways of representing these things. So instead of, because a lot of people don't want to write L1, so they'll call this, we'll call it A. And how can we define A as a line? Well, above the A, you put a line with arrows on both sides. So A represents this entire line here, going from this way down as far as you can go to that way as far as you can go. What other things can we define here? So that's a line. So A is a line. Let's call B starts from here and goes on forever. What's that called? If it starts at one point and goes on infinitely. Very good. Array. So array starts at a point and goes on infinitely. So with array, we only have an arrow on one side. Typically what we do is since the ray of B is going from here to the right, it's point to the right. If it was going from this point down, we'd have it point the other direction. So the way you're pointing on top of that letter tells you the direction that ray is going. Now, how about if I start here and end here? What's that called? What? A line segment. We'll call that C. So this is B. How do we represent a line segment? It's just, it doesn't have arrows on both sides because it starts and stops at a solid point. It's finite in distance. So a ray starts at a point and goes on infinitely. A line segment starts and ends at points, and line just goes on infinitely both directions. How many of y'all heard those before? I know everybody has. Again, in this course, you're gonna remember a lot of stuff that you never heard about, don't remember hearing about. So we had two dots. If you have 2 points, you can find the following. So if I had 2 points, what can I find? What's that? Slope. We can find the slope between those 2 points. What else? Equation of the line. The y-intercept. What is the y-intercept? Yeah, it's where the line crosses the y-axis. Do we always have to have a y-intercept? No. What else can we find? Give you a hint. There's 3 left. We found the y-intercept. What other intercepts do we find? We can find the x-intercept. That's where the line crosses the x-axis. Two more big things. That's not a line. If it bends, it's not a line. A line has to stay the same. The definition of a line is the ratio between any 2 consecutive points is always the same. Basically, the slope between each 2 points is the same. So it has to be straight. 2 more things. The midpoint between the 2 dots and one more. Starts with a D. Ends with instant. The distance between the 2 points. So to do this, we have to pretty much start in this order. Well, in our order, we're going to do this first. Then we'll find the midpoint, and then we'll find the distance, and then we'll find everything else. And it all happens with the same basic information. So let's begin with slope. Everybody okay? Slope. We use the letter M, little m, to represent the slope. How would you define slope in words? Very good. Rise over run. That's the typical definition people give, but it's not accurate. It's somewhat accurate. If it says rise, what direction does that go? If I say run, which direction does that go? To the right. Well, remember, rise is up and down, and when you run, it's horizontally. But rise only goes up. Can you go down?
No.
So a line that's going up is like this. A line that's going down is like this. So it can go up or down. We call this a positive slope. We call this a negative slope. So I like to say it's rise or sink over run. It's rise if it's positive, it's sink if it's negative. And the bottom is always positive. It always goes to the right. Whenever you have a fraction, the bottom number can never be negative. So if you had a fraction that looked like this, move that decimal, that negative sign either in front or on top. You never want to have the negative on the bottom. And this will be apparent next week or next time when we talk about the fractions. When we add subtract fractions. So now when we talk about, and just for simplicity purposes, we'll look at this. Rise over run. Basically what this means is the vertical change over the horizontal change. Vertical goes up and down. Horizontal goes left and right, or in our case, always to the right. How do we determine the change of something? In other words, change, the word change means the difference. In mathematics, we call that delta, and it's represented by the triangle symbol. So whenever you see in any textbook, anything, if you see a triangle, that means the change. So what we would do is the vertical change over the horizontal change. That's more mathematical looking. So the difference. How far is it from 3 to 9? How far is it from 4 to 28? How far is it from 12 to 97? How'd you get that? Exactly. So to get the first one, you took 9 minus 3, you got 6. 28 minus 4, got 24. 97 minus 12, got 85. So here's the first number, and here's the second number. So what do you always do? What does each one of these tell us to do? Take the second number minus the first number. So if I had x1, here's my first x, and here's my second x, what do I do? How far are they apart? Sure you do. Same formula you've been using. X2 minus x1. The second point, second number minus first number. It's the same you've always been doing. It also works with the y's. How far is it from y1 to y2? It's the second number, 97 minus 12. 28 minus 4. X2 minus x1. So this one's going to be that's the change. So what this tells us, the change in the vertical is y2 minus y1 over x2 minus x1. And there's your slope. Oh well. And that's it for today. Or do you want to do an example? Let's do one example real quick. We have 1 minute. So let's look at our 2 points. We have 1, 1 and 5, 4. What's the slope between those 2 points? The first thing you have to do is label x1, x2, y1, y2. Well, we know that 1 and 1 is our first point. So that's point 1. The subscript tell us it's the first point. 5, 4 is the second point. So therefore, this is the x value of the first point. That's x1, y1, x2, y2. So the first thing we do is just label all our points. So we have x1 is 1, x2 is 5, y1 is 1, y2 is 4. Once you label them, it's a matter of plug and play. 4 minus 1, 5 minus 1. And there's your slope. And this is where we have to call it a day.